In this presentation, I will describe some mathematical consideration in doing time domain simulation. I understand that mathematics may be very tedious, but it is not that complicated. It is like learning a new language that you may not be able to understand everything in the first exposure, but you will naturally get it if you persist and go through the material a few times. However, if you just want to get a very general idea of the subject, you may jump to the solution and skip all the intermediate steps. You can pretend to be an expert if you can speak the technical language. For example, mentioning the forward Euler and backward Euler integration method in circuit simulation. This presentation focuses on single-step integration algorithm. Let's first define what is a single-step integration method. It means the numerical solution of the differential equations at time ti only depends on the solution at time ti minus 1, and not the solution at earlier time points. We will cover multi-step integration algorithms that make use of solutions at time points beyond ti minus 1 in the next presentation. So far, all integration methods we learned, including forward Euler, backward Euler, and trapezoidal rules, all belongs to single-step integration method. When we perform integration over multiple time points, errors will accumulate. We have to find a way to estimate the error so as to ensure the accuracy of the simulation results. To do that, let's assume the solution at ti minus 1 is exact. Let's call the exact solution at time ti VETI. Apply Taylor expansions to VETI about the time ti minus 1. We have the following series. Assume a single-step integration algorithm gives an approximate solution VATI. Then, the errors of the algorithm is given by epsilon ti, which is equal to VETI minus VATI. Using this approach, we will look at the error resulting from different integration methods. Let's start with the forward Euler integration. The approximate solution provided by forward Euler is given by the equation here. Recall that the exact solution VETI after Taylor expansion is given by the infinite series here. The error is obtained by subtracting VATI from VETI, which is given by the series here. From the property of Taylor expansion, there is a time point t psi between ti minus 1 and ti, such that x squared over 2 factorial times the second time derivative of VE at t psi is equal to the error term. That is, the error in forward Euler is bounded by x squared over 2 factorial times the second derivative of the solution at some time point between ti minus 1 and ti. Graphically, the approximate solution obtained from forward Euler is given here when the function is monotonically increasing. And it is given here when the function is monotonically decreasing. In both cases, the solution at time t1 is estimated by the value at time t0, plus the increment estimated from the derivative at time t0. And it is similar for the solution at time t2, which is estimated from the solution and derivative at time t1. You should notice that the solution is at the exterior of the curvature of the solution curve. This property makes the forward Euler integration method less stable, which will be discussed shortly. The error of the integration depends on the step size h, which is given by the equation here. If a large step is used, it may lead to significant error as shown in the figure here. We will discuss the considerations for selecting h shortly. After studying the error in the forward Euler integration method, We apply the same approach to study the error in the backward-Euler integration method. The approximate solution provided by backward-Euler at time ti is given by the equation here. In this equation, the approximate solution at time ti depends on its exact derivative at time ti, which has not been solved yet. So we have to find out what it is from earlier solutions first. Recall that the Taylor series of the exact solution at time ti is given here. We can differentiate this equation with respect to time to obtain the Taylor series of the exact voltage derivatives at time ti as shown here. So we obtain an expression for the exact derivative at time ti. Using it and the exact solution at time ti, we can write the approximate solution in the form of infinite series given here. Subtracting it from the exact solution will produce the error terms given here. Again, from the property of Taylor expansion, we can find a time t psi where the error terms equal to minus x squared over 2 factorials times the second derivative of the exact solution at t psi. Graphically, the approximate solution obtained from the backward-Euler integration is given here, when the function is increasing monotonically. And it is given here when it is decreasing monotonically. In both cases, the solution at time t1 is estimated by its value at time t0 and the increment estimated from the time derivative at the current time point t1. And it is similar for the solution at time t2, which is estimated from the solution at time t1 and the derivative at time t2. You should notice that the solution is at the interior of the curvature of the solution curve and confined by the function. This property makes the backward-Euler method more stable. The error of the integration depends on the step size h, which is given by the equation here. If a large step is used, it may lead to significant error as shown in the figure here. Finally, we will look at the error in the trapezoidal rule. The approximate solution provided by the trapezoidal rule at time ti is given here. Substituting the time it derivative at time ti with the infinite series derived from the backward-Euler integration method, we have the approximate solution given here. Subtracting it from the exact solution, we obtain the error term given here, which starts with the third derivative of the exact solution. As the error in the trapezoidal rule is proportional to h to the power 3, its error is much smaller than both the forward-Euler and backward-Euler integration methods with small h. After studying the error bounds of the different integration methods, we have to answer the questions on how to select the step size h. In addition to accuracy, it is also related to the stability of the single-step integration method. Consider the general differential equation in the form of dv dt equal to some constant lambda times the voltage. Regarding it as an initial value problem, we define the initial value at time t0 equal to 0 to be a known value v0. In a circuit equation system, Vt and lambda are usually in vector and matrix form. But we will use the formulation in 1D to illustrate the basic concept. For such general differential equation, the exact solution is equal to v0 times the exponential of lambda times t. For example, in a RC circuit, lambda is just equal to 1 over RC. Now, let's apply the forward-Euler method to perform successive evaluation for the given differential equation. With the solution at time t0 given, We have the solution at time t1 given here, using the forward Euler method. At time t0, the voltage is just the initial value V0, and the derivative is given by the differential equation at time 0, which is lambda times V0. Therefore, Vt1 can be given by the following equation. We can then evaluate Vt2 in terms of Vt1. As Vt1 has already been solved in terms of the initial values, we can replace Vt1 with the solution consists of only V0, lambda, and h as given here. The process continues to time ti, of which the voltage is given by the expression here. As we expect the solution to be finite at all times, even with very large I, we need the magnitude of the term 1 plus h times lambda to be less than 1. As the time intervals has to be positive, lambda has to be negative to fulfill the requirement of 1 plus h lambda to be less than 1 in magnitude. Physically, positive lambdas means the system has positive feedback, and the equation will blow up. Based on these conditions, the range of possible h for the integration method to be stable is between 0 and -2 over lambda. Graphically, it can be illustrated in the diagram here. When h is between -1 over lambda and -2 over lambda, the solution oscillates to 0. When h is equal to -1 over lambda, Vti equal to 0 for all I. This is useless. As a remark, I would like to point out that stability does not guarantee accuracy, but it is an important condition to fulfill. We can also apply successive evaluation to study the stability of the backward Euler method. But we will skip some mechanical derivation steps to keep these presentations concise. From the backward Euler equation given here, we can express Vt1 as V0 divided by 1 minus h lambda. Following the successive evaluation process, we can express Vti as V0 divided by 1 minus h lambda to the power I. For this expression to be finite at very large I, we need the magnitude of 1 minus h lambda to be larger than 1. Again, lambda needs to be negative to have a stable feedback system. The stability region for h is illustrated in the figure here. We normally will not consider the region of negative h, as we do not want to deal with negative time. As the stable region covers all the values larger than 0, we can say that the backward Euler method is absolutely stable for all positive value of h. For h larger than -2 over lambda, the solution will converge in an oscillation fashion. To satisfy both accuracy and stability, h has to be positive and close to 0. The stability condition of the trapezoidal rule can be derived in the same way. To avoid all the detailed mathematical derivation in this short video, I will just show the solution of Vti from the successive evaluation method here. The process is the same as what we have done before, and it is very mechanical. Based on the expression obtained, the stability condition is given here, together with its graphical representation. Again, it is stable for all positive values of h. But the convergence will be oscillating if h is larger than -2 over lambda. Sometimes, a system with the presence of both capacitors and inductors may result in second-order differential equations. it may require the use of complex variables in the solution. In such situation, the successive evaluation method can still be applied, and the stability condition is governed by the magnitude of the H-lambda product. I will not perform the detailed derivation, but just to point out the stability regions of the H-lambda product for different integration methods. Please note that in this situation, we are spanning through the complex plane. Therefore, we express the stability region in terms of the H-lambda product instead of just the integration interval H.